Now that we understand how to calculate binomial probability, let's look at the binomial distribution. Remember, in probability distributions, our random variable x represents all the possible, represents a numerical outcome. Here it will represent the number of successes. For each of those, we're going to have a probability. So here, in this example, if we roll a fair die 3 times, and we'll consider success to be rolling a number divisible by 3. So here, success means that we roll a 3 or a 6. And so then the probability of success is going to be two out of the 6, because we have 6 outcomes when we roll a die, so 1/3. Therefore, the probability of failure will be 1 minus 1/3, which will be 2/3. So we have our P and we have our Q. How many trials do we have? 3, because we're going to roll the die 3 times. So now we can make a probability distribution table. So remember, we're going to let x be the possible values for our random variable. So here that'll be the number of successes. For each of these we should be able to calculate a probability. In 3 trials, how many successes could we possibly have? We could have 0, we could have 1, we could have 2, or we could have 3. What's the probability of getting 0 successes? Well, we would do combination 3, 0. Probability of success will be 1/3. Raise that to the 0th. Multiply by 2/3. Raise to the 3, because if we have 0 successes, we'll have 3 failures. And this should give me about 0.30. Now let's suppose that we have 1 success. So here, out of the 3 trials, I'll choose 1 to be successful. Then I'll have 1/3 to the first, and then 2/3 to the second, because I'll have 2 failures. This turns out to be about 0.44. Combination 3, 2. 1/3 to the number of successes, so 2. 2/3 to the number of failures, so 1. This is about 0.22. And last, combination 3, 3. What's that going to be? That means we're going to choose the whole entire group. How many ways is that possible? 1. So that'll be 1/3 to the number of successes, so 3. 2/3 to the number of failures, so 0, which is about 0.04. Let's do a little check on ourselves. Our sum here should be 1. So that'll be 0.74, adding the first 2, then about 0.96. The sum should be 1, although if you're just writing these down and you write down rounded values, it could be possible that when you add the rounded values you don't get 1 exactly, but it should be extremely close. Now we could draw a histogram. So here, and we're going to go ahead and put 0 on our x-axis like this, because that is a number of successes. 1, 2, 3. Possibilities here are 0.1, 0.2, 0.3, 0.4, 0.5. We're going to consider these x values to be the centers of the bars. So this first bar will go up to 0.3. Next one will go to 0.44. And then 0.22. and then 0.04. So our histogram will look something like this, and sometimes you'll see the probabilities written on top of the bars like this. So this histogram describes our binomial distribution. Now to find our expected value, we could multiply each of the probabilities by the corresponding value for x and add those up, and that will give us our expected value. It turns out adding it up for 4 different possibilities like this would not be bad, but what if we had 200? We certainly wouldn't want to calculate every single probability for 200. That'd give us 200 formulas, multiply each of them times the x value and add them up to come up with our value for the expected value. Let's go ahead and determine the expected value here. So we would take 0, and this will be an approximation here, times 0.3, and then we'll do 1 times 0.44, and we'll do 2 times 0.22, and then we'll do 3 times 0.04. And so this will turn out to be 1 in our case if we used exact values. If you think about it, does that seem reasonable? Probability of success is 1/3. We roll it 3 times, so how many of those 3 would you expect to be a success? I would think 1. And that turns out to be the case. Expected value of the binomial distribution. All you do, you take the number of trials, multiply by the probability of success. That tells you the expected number of successes in n trials. It's a very simple formula. Let's look at this one. If we roll a single fair die 10 times, and we're going to consider 4 to be a success. So here, the probability of success would be 1/6, because on my roll of dice, if I roll 1 die, I have 6 possibilities, all equally likely. There's only 1 in my event, which is the 4, so we get 1/6. And then my Q would be 5/6. And what is my N, my number of trials? My N is 10. So here, my expected value be NP, so that'll be 10 times 1/6, which is 5/3, which is 1 2/3, so that's about 1.67. So while we know it's not possible for 1.67 successes to be achieved in 10 trials, in other words, only integer numbers of successes are possible, it certainly seems reasonable that about 1/6 of the time we will have a success. We take the 1/6 and we multiply it by 10. Our expected value then is considered to be 1.67. Let's suppose that we have a certain medical treatment for cancer that's found to be effective 63% of the time in patients. If we have 300 patients undergo the treatment, what's the expected number of cases which the treatment is effective? Sorry, the treatment is effective. So here, the probability of success would be 0.63, and therefore, what's the probability that the treatment is ineffective or unsuccessful? 1 minus 0.63, which would be 0.37. Although we don't really need that for this problem, because all we are being asked is what is the expected number of cases in which the treatment is effective? So the expected value then will be NP, which will be 300 times 0.63, which will be 189. In other words, we would expect it to be effective in 189 out of those 300 patients. Let's suppose that we have an exam with 10 true-false questions. Let's also suppose, of course this would not happen, but let's suppose that you haven't studied all semester, so your only choice is to randomly guess at each question. You need a 70% to pass, and we want to determine your probability of passing by randomly guessing. So if we have a 70%, since we have 10 questions, that means that we have 7 of our 10 are going to be correct. We know this is a binomial distribution because we have the same thing happening over and over again on each question we guess. So we have 10 trials, and we have a fixed probability of success on each one, and all our trials are independent. On one question, what is the probability of success? In other words, each trial will be one question. Probability of success will be that you guess correctly. And if you truly are guessing randomly rather than making educated guesses, then your probability of success will be 1/2. And your probability of failure will also be 1/2. So we want to calculate the probability of getting at least 7 correct. So 7, 8, 9, or 10 would be a passing score. So we're going to have a separate formula for each one. So we could have 7 correct. We could have 8. We could have 9. And we could have 10. So here we get combination 10, 7. We have 10 trials. We'll choose 7 to be correct. 1/2 to the number of successes. Then the probability of failure, which is also 1/2 to the number of failures. Then we're going to have combination 10, 8. 1/2 to the 8th. 1/2 squared. Combination 10, 9. 1/2 to the 9th, 1/2 to the 1st, and then one last formula. Combination 10, 10. 1/2 to the 10th, 1/2 to the 0th. In other words, all 10 correct, and that means there will be 0 failures. Now, one thing that you can notice on this particular one, and the only time this will happen is when both of our probabilities are 1/2, notice in each term we have 1/2 raised to the 10th. In other words, we can factor out 1/2 raised to the 10th out of the whole thing. And then here we're going to have combination 10, 7, combination 10, 8, combination 10, 9, and combination 10, 10. Combination 10, 9 will be what? How many ways can I choose 9 out of the 10 to be successful? Well, every time I choose 9 to be successful, that means I'm choosing 1 to be left over. How many ways are there to choose the 1 left over? 10. How many ways are there to choose all 10 out of a group of 10? 1. So keep in mind those when you are doing your calculator punching. You don't want to be putting in a bunch of unnecessary calculations when we should just notice that this is 10 and that this one is 1. And we factor out our 1/2 to the 10th. You should end up with 0.17185. That's the probability that we pass a true-false test by guessing if there are 10 questions. Now let's make it a little bit more difficult. Let's suppose that our test is multiple choice and that on each question we have 5 choices. So here, my probability of success on a given question would be 1/5, which would be 0.2. My probability of failure then would be 4/5, or 0.8. Once again, for 70%, that would give me 7 successes, or 7 correct questions in our 10 trials. So here we want the probability that x is greater than or equal to 7. So that means the probability that x is 7, x is 8, x is 9, x is 10. We're going to add all these up. For each of them, we're going to have a separate formula. Combination 10, 7. This is going to look just like the one above, except our p and our q are different. So here we have the probability of success, 0.2, raised to the number of successes, which is 7. Probability of failure, which is 0.8, raised to the number of failures, which is 3. Combination 10, 8, 0.2 to the 8th, 0.8 to the 2. If I have 8 successes, I have 2 failures. Combination 10, 9, 9 successes, so 1 failure. And then last, combination 10, 10, which remember will be 1. 0.2 to the 10th, therefore 0.8 to the 0th. Remember, any non-zero number to the 0th is 1, so we could put in 1 for that as well as for here. Punch these in. I'm just going to write down the numbers for each so that you can check yourself. You'll see we get some pretty small numbers here. And notice with each term they're getting smaller because it certainly is less likely to get 10 successes than to get 7. Would you not agree? If we add all these up, we get about 8.6435 times 10 to the negative 4, moving our decimal point. That will give us 0.000864. So this is definitely not a good way to approach taking an exam. Okay, I hope this helped you to understand the binomial distribution. Good luck, and we will see you next time.